Alright, so we are just going over the homework, and they were application vector problems. And I'm going to do it backwards, so they should seem to get easier. Starting with number 59, a force is given by the vector F equals 3I plus 2J. And as you guys all know, that can just be rewritten as 3, 2, correct? And the force moves an object along a straight line from the point 4,9 to the point 1020. Now yesterday I very quickly gave you 3 different equations for work, that are, or a couple of different equations for work, I forget how many now, that are all based on the idea that work is force times distance. You guys remember that idea, right?
Yeah.
Okay, the simplest of these equations, there's 2 very simple forms of it. One, if you're only talking about one dimension, if you're just pushing a force, using a force to push an object for distance, and both the force and the path are parallel, then you're just going to multiply the force times the distance. Life is good. If you are in another situation, you might have to use a vector projection. But if you can describe both the force and the path, the distance, as vectors, then all you have to do is the dot product. Now we're given the force as a vector. Are we given the path along which the force is applied? I mean, is that you're pushing on this object and it's moving a distance. Were we given this as a vector?
No.
No, it's going from point A to point B. Can we turn that into a vector?
Yeah. With the
What is the vector that connects this point to this point? How would we find that? Tim, Trey, you with us on this one?
6 would be
Where would the 6 come from?
because it's from 4 to 10. It's 6.
Yep, 10 minus 4.
And then 11.
And then 11, 10 minus 9. So we can take this path and write it as the vector 6, 11. And then the work done is just going to be the dot product between 3, 2, dot 6, 11. So that's 3 times 6 plus 2 times 11. And that is 18 plus 22, which is 40. 40 what, you might ask? And we'll find the work done if the distance is measured in feet and the force is measured in pounds. So that's 40 foot-pounds of work. It means the amount of work done to move a 1-pound object 40 feet, or 4-pound object 10 feet, or 40-pound object 1 foot. So if you have the path described as a vector and the force described as a vector, you do the dot product between them, you get the work done moving that object along that path. Any questions on that one?
No.
Again, you've got a situation where the work is not parallel, the force is not parallel to the path followed by the object, so it's kind of like that sailboat and other examples we talked about yesterday. I'm going to leave this up for a second and go over here to talk about number 57. Alright? You're getting good at this. Alright, number 57. 57 describes a ramp going up at 12 degrees. There is a box being pulled up the ramp by a rope, but the rope is not going parallel to the ramp. That's a 12-degree angle. Now, they give this total angle here from the rope to the horizontal as 38 degrees. So if that's 38 degrees and this is 12 degrees,
26.
there's a 26-degree angle in there. Now before you find out the work, you got to find the force. The question is again about, it says a force of 60 pounds, make this a whole vector. Your force of 60 pounds on a rope is used to pull the box up the ramp, inclined at 12 degrees from the horizontal, that's the ramp. The figure shows the rope forms an angle of 38 degrees with the horizontal. How much work is done pulling the box 20 feet along the ramp? We can ignore a lot of this. We can just say this is a 60-pound vector acting on an object at 26 degrees above its path. So the force the object actually feels, how did you describe it earlier, Tim? The force that the box accepts?
Yeah.
Yeah, the force that the box accepts is going to be whatever part of the 60-pound force is projected onto the path of the box. So that's going to be 60 pounds cosine 26 degrees. That's your force in pounds. How far up the ramp does it go? 20 feet. So the work done in this case is 60 pounds cosine 26 degrees times 20 feet. And what's that final answer? Who got that?
Alright, oh, sorry.
Tim, you worked it out, I think.
1,200 pounds.
1,200 pounds is the work you do pulling up the rope. Then you multiply that by cosine 26 to find out how much work the box accepts of that.
Oh, 1,078 pounds.
That's right. So the work done on the box is 1,078 pounds. Now what Tim was saying about the 1,200 pounds, that's just the 60 pounds times the 20. If you pull with 60 pounds over a force of 20 feet, that would be 1,200 pounds of work, but that's not what the box feels because you're pulling at an angle. Box only feels 1,780 pounds of it, or accepts that much
Where
work.
did you go 20 feet from?
Oh, I'm sorry, I didn't, the rest of the problem said, the final question was, how much work is done pulling the box 20 feet along the ramp? So, we know the force is 60 pounds cosine 26 up the ramp. You go 20 feet along there, in that direction. We'll break this down a little more specifically in physics in a couple of weeks. Any questions on 57? So we didn't have to pull out that really hideous vector projection formula. We could have done that if we figured out a path vector. If we had just said, what is that vector described as a path, we could have projected this one onto it with that worse formula, and that wouldn't be that hard to do, because it doesn't matter how long the vector is. So we could have just said 1 cosine 26, 1 sine 26, and used that formula, but I don't think that would have been easier. Any questions on 59 or 57? Nope. Good. Okay. The next ones were determine whether V and W are parallel, orthogonal, or neither. And we went to number 49 for that, and they said vector V is 3i minus 5j, and vector W is 6i plus 10j. The formula we used yesterday said the cosine of the angle between the vectors was V dot W over the magnitude of V times the magnitude of W, right?
Mm-hmm.
Is that correct?
Yes.
Okay, good. So that's going to be 3 times 6 plus negative 5 times 10 over Pythagorean theorem times square root of 3 squared plus negative 5 squared multiplied by the square root of 6 squared plus 10 squared. Is that correct?
Yeah.
Okay. Then that's going to be 18 minus 50 over root 34, 25 plus 9, times root 136. So that's negative 18 minus 50 is 32. Negative 32 over root 34, root 136.
I think you.
Double check.
That one set called 49. I think that you're doing 47. Yeah.
You are correct. I am doing 47.
And then
Did I use the correct two vectors?
6 squared plus 10.
You used it correctly.
But isn't 6 squared plus 10 squared, you get 3600? Or wait, no, that's multiplied together. Oops.
Yeah, it's multiplied together. Whoops,
Yeah.
no you don't. No you don't. Okay, so we were, gotcha. I didn't catch that before when you and I talked about this problem. Yes, you do get 136. Okay. Do I need a calculator to finish this problem?
No.
You probably don't.
Thank you, Diego. Appreciate that. If they are perpendicular, if they're perpendicular, two vectors, then the cosine of their angle is 0. Why? Because if they're perpendicular, they either form an angle of 90 or 270, and the cosine of 90 and the cosine of 270 are both 0. If they're parallel, the cosine of the angle between them is either 1 or -1. Because the cosine of 0 degrees is 1, cosine of 180 degrees is -1, and two vectors will be parallel if the angles between them are 0 or 180. Do I need a calculator to answer whether this is 0 or 1 or -1?
No.
No, neither of these are perfect squares. It's not going to break down to -1 or to 0. So this one is neither. This is a totally fair non-calculator question. You don't actually have to find the cosine or work out to simplify the radicals or anything. You can stop there. Arguably, you could have stopped here, or maybe even here if you're really good. Any questions on that one? All you need to be looking for is 0, 1, or -1.
Can you do one of the 43 or 44 problems?
I like to do 49 and then do those, yeah.
Ooh.
Those might be a little easier than you think. But follow me back this way when you can, Diego, and we'll... Now I'll do 49. Tim will double check if I copy it down correctly this time.
Yeah.
V is 3i minus 5j. W on this one is 6i plus 18/5 j. Cosine theta is 3 times 6. Here's my dot product on the top. Minus 6 times 18 over 5 over the square root of 3 squared plus,
Minus 5 times 18
thank you, minus 5 times 18 over 5. Excellent. Double check me on those details. And 6 squared plus 18 over 5 squared.
But the top cancels out.
Yeah, I don't have to care about this bottom because I'm going to get 3 over 6. The 5s will cancel that. 3 times 6 minus 18 equals 0. I have 0 in my numerator. Do I even care what my denominator is?
No, because
No.
it's automatically orthogonal.
Boom.
Orthogonal.
Perpendicular, or that fancy word for perpendicular in more than 2 dimensions, orthogonal. Not one of my favorite words. I'm going to take another quick look at 47, show you guys a shortcut though. It's good to know that cosine formula, you need to know it, but there is a quick thing you can check. Vector V was 3, 5. Vector W was 3, -5, excuse me. Vector W was 6, 10. Okay, so we had to check the angle to see if they were orthogonal or not. What if vector V, let me do this as a separate example. What if vector V had been 3, 5, and vector W was 6, 10? Would you have to pull out the cosine formula to tell me whether those vectors are parallel or not?
No.
No? What do you think they are?
Wait, to tell you if they're parallel? or
Yeah,
not?
tell me if they're parallel. Forget about orthogonal, but
18, I can't see anything.
well, the dot product won't be 0, so you can't talk about perpendicular. But remember how I said vectors, you could look at the components kind of like slope?
Yeah.
So this is a vector that goes over 3 and up 5 and looks like that. This is a vector over here that goes to the right 6 and up 10. Do you have enough information to tell me if those hypotenuses are parallel? Yeah? If this were a line, what would its slope be? Rise over run.
Yeah. So 5 over 5
And if this were a line, what would its slope be? 10 over 6. What's 10 over 6 reduced to?
Sorry, wait a minute. 3 or 5 over 3.
Yep, 10 over 6 does equal 5/3. These vectors have the same slope.
So that means that.
That means they're parallel. This vector is exactly twice this vector, and they go in the same direction. So you don't, if the question is just, are these vectors parallel, do you have to pull out that cosine formula?
No.
No. So we could have looked at 3, -5, and 6, 10 and said, oh, they're definitely not parallel because these vectors, these components, aren't a multiple of these components. What if this had been -6 and -10? Would the vectors have still been parallel?
No. Yes.
Yes, they actually would have been. The vector would have been going in the opposite direction, but these vectors would still have been parallel if this was 3, 5, and this was -6, -10.
What if it's like 3, -5, 6, -6?
3, -5, 6, -10. Let's look at it. Diego, follow me back over this way.
That's number 45.
Let me just make sure I heard you right. So you said, for example,
No, it's number 45.
oh, 3, -5, and then the next one is what?
6, -10.
6, -10. Okay, so this is a vector that goes 3 units this way, 5 units down. Looks like that. And the rise over run is -5 over 3. This is a vector that goes 6 units right, 10 units down. Vector looks like that. The rise over run would be -10 over 6. If they were lines, would they have the same slope?
Yeah.
Yeah, they're parallel. You do not have to pull out the cosine formula at all. Does that make sense?
Yep.
So checking if vectors are parallel is actually pretty easy. Does this help you at all? Are there any quick tricks like this to see if they're orthogonal? No, they're not. You have to do the dot product and see if you get 0. Are there any tricks like this to see if it's any other angle? No, you have to pull out that cosine formula. Does that make sense? All right, now let's look at the ones from, what were they? 43 and 44? There's an Easter egg in these.
Really?
Yes, there was. Remember how I mentioned if you're looking at a vector, if you're given the magnitude of the vector and the angle of the vector. I wanted you guys to just start thinking, take that magnitude, multiply it by the cosine, and that's your horizontal component. Take that magnitude, multiply it by the sine, and that's your vertical component, right? I even said, sometimes I don't even care if you leave the answer like this. If this were 5 with magnitude and that was 30 degrees, 5 cosine 30, 5 sine 30, that's the important part, that you see that relationship, okay?
What's the magnitude though?
Pardon?
What is the magnitude that they give us?
Well, let's see what they give us. They say, for number 43, they say vector v is 2 cosine 4 pi over 3, comma, 2 sine 4 pi over 3, right?
Yeah.
Magnitude of v, 2 and 2. Cosine of theta, sine and theta. Cosine 4 pi over 3, sine 4 pi over 3. This question asked you to take the way I asked you guys to think about this a certain way when you're given the magnitude and the angle. This question asked you to do that backwards. Now, if you worked out the cosine formula, you should have gotten 120 degrees, or I'm sorry, 4 pi over 3 is 240 degrees.
Oh, I'm sorry. I think you're forgetting vector sign because you have one at the end and no beginning.
Thank you, I left off that bracket, awesome. Like I said, double check me on the details this rainy Friday. If you worked out the formula, you should still get an angle of 240 degrees between them, 4 times 4 pi over 3. And if you did the Pythagorean theorem, you'd get a magnitude of 2. But they asked for, find the angle in degrees between v and w. Well, theta in radians is 4 pi over 3, so in degrees that is 240 degrees. Does Does that make sense?
Yeah, so what you would have to find that, right?
You would, but they just, I mean, if they give it to you in the form where it's cosine and sine, it's this theta has to be the angle between them. And this number always has to be the same. Because every vector written in component form must have come from a magnitude multiplied by a cosine, and that same magnitude multiplied by a sine. Does it always look like this? No. This is spelled out very nicely for you. So for 44, the vector they gave was 3 cosine 5 pi over 3, comma, 3 sine 5 pi over 3. So what's the angle
No,
between?
you have to do, no, you haven't done the whole problem though. You have to find it between V and W. You only found what the degrees were for W.
Yes, I did. So okay. Oh, you're right. I'm writing this down from the wrong problem. Thank you. So that's 240 degrees. And then for the next one they give for W. Thank you, Trey. It says 3 cosine 3 pi over 2, right?
Yeah.
Comma 3 sine 3 pi over 2. So what's theta? This is theta for V. What's theta for W is how many degrees is 3 pi over 2? Okay. So what is the, how many degrees are in between these two angles?
30.
30 degrees.
So when I did the cosine equation, I did a whole bunch of crap I didn't need to do, and I still got 30.5.
That would have been a rounding error, yeah,
Yeah.
in there. It turns out to be exactly 30.
Yeah.
Yes. But you did do, as you put it so well, a whole bunch of crap you didn't have to.
Yeah.
It turns out there was a big Easter egg on this one. But we haven't talked about how this relationship much. When we get to polar coordinates and the complex plane and a couple other things, we're going to talk a lot about how if you're looking at something and you see the cosine and you see the sine and you see a magnitude, you can break it down from there. So there's a 30-degree difference between them. So looking at number 40, looking at number 44, they've got 5 pi over 3 and pi. All you have to do is find the difference between those two. You can see the angle in the vector in this form. Any questions on that one?
No?
Okay. The homework tonight, which I'll let you guys start in one sec, but I want to read it over here, is same sheet, 46, 48, 50, and I'm going to add in,
52.
hold on,
Wait, so 46, 48, 50.
yes, and I'm going to give you also 62. And we'll talk about some more of these on Monday. All right? Kill it, Diego.